Hey everybody, Corey and Victoria here. We are the Professors DuBois, and in this lecture video, we are going to expand on our previous video where we introduced quantum numbers. And if you remember, we talked about the quantum numbers N and L. So in this video, we're going to expand on that a little bit, give you a little more exposure, and we're going to introduce a third quantum number, which we're going to call M sub L.
Yes. And that is the magnetic quantum number. So M sub L is the magnetic quantum number, and possible M sub L values range from negative L to positive L, and that includes zeros. These are integers. So when L is when L is 1, M sub L can be -1, 0, or 1. When L is 0, M sub L can only be 0. If L is 2, M sub L can be -2, -1, 0, 1, or +2.
So I know L was giving us the shape. So what exactly is this M sub L even giving us?
Yeah, M sub L tells us the number of orbitals that can exist because they're in different orientations. So we can think about this X, Y, and Z axis when we're talking about the p orbitals. So p orbitals were our dumbbell orbitals when L equals 1. So you can think of one running in the X direction, you can think of one running in the Y direction, and then you can think of one as the Z direction, kind of coming in and out of the plane of the screen here.
So L equals 1 was the dumbbell, so the M sub L could be -1, 0, or +1. So there's 3 different spatial arrangements.
You got it. So here it's shown in a little bit of a graphic here. So this is saying 1s. This is a 1s orbital. And bringing back the N and the L from our previous lecture, when it's a 1s orbital, that means that N equals 1 and L equals 0. Well, when L equals 0, M sub L can only be 0 because it goes from -L up to +L.
This makes sense because a sphere doesn't really have different arrangements in space. No matter how you turn or rotate it, it's still a sphere.
That's right. When L equals 1 for a p orbital, M sub L can be -1, 0, and +1. And that's why we have 3 different p orbitals for any given n. X-axis, Y-axis, and Z-axis. You can see this a little bit better here.
And that was N equals 2 for those in the box.
Yeah, so this was N equals 2. So if we move up to the N equals, why isn't there, I wonder why there's not a D orbital here for the N equals 2. Let's come back to that. When N equals 3, we have L can be 0, L can be 1, or L can be 2. So there is a 3s orbital, there are 3 3p orbitals, and there are 5 3d orbitals. And where do those 5 come from? It comes from the M sub L. M sub L can be -2, -1, 0, +1, or +2. Those are 5 different orbitals that M sub L tells us. And these are 5 different orientations for that clover leaf, and then this kind of funny one here. So 3 different quantum numbers define the orbital. If you know the N, the L, and the M sub L, you've narrowed it down to one individual orbital. And each of these orbitals, and each atom has many, many, many of these orbitals kind of piled up on top and overlapping each other. But any one given orbital can hold 2 electrons. And for any given n, there are n squared of these orbitals. Now coming back to, why don't we have a D for n equals 2? When n equals 2, L can be 0, 1, 2, 3, 4, up to n minus 1. Well, n minus 1 is 1 for the n equals 2. So we don't have an L equals 2.
We could have a sphere or a dumbbell shape.
Yep.
For n equals 2.
So we only have 4 orbitals when n equals 2. All right, so let's kind of break this down.
So this is just a series of questions. We're starting out with a given, n equals 3. Now you remember, we can look at the periodic table, and n can be equal to 3 for the main group elements in period 3. In the transition metals, we have that first period is period 4, but the transition metals are period -1, so that first period of the transition metals could be in n equals 3, and that's it. So we want to know how many orbitals are there, and you've already alluded that there can be an awful lot. I hope there's a trick. How many total electrons can be held, and what are the quantum numbers for the orbitals?
So the trick was n squared. So 3 squared is 9. So we have 9 different orbitals, and each of those orbitals is an address with 3 quantum numbers tell us that address. Double the amount of orbitals is the number of electrons, because each orbital can hold 2 electrons. So, but the third one, what are the quantum numbers for each of these orbitals? And we're going to have 3 for each of these orbitals. So let's kind of dissect n equals 3. When n equals 3, L can be 0, 1, 2, up to n minus 1. n minus 1 is 2. So our highest L value is 2. Recall from our previous lecture that when L equals 1, that's an s orbital. When L equals 2, what did I say?
You said 1.
I said 1. L equals 0 is s. L equals 1 is p. I got ahead of myself. I got excited. L equals 2 is the d orbitals. So now we can break it down. Now we understand that we have another quantum number, m sub L. So we can break down the L's into each possible m sub L. Go ahead.
Okay, so when we have L equals 0, m sub L can be negative L to positive L. But since it's only 0, m sub L can only be 0. There is just one arrangement in space for this L equals 0, or this spherical orbital. When we get to L equals 1, m sub L could be negative L to positive L, including 0. So we have negative 1, 0, and positive 1. That's 3 different arrangements, and these are the dumbbell-shaped, the p orbitals.
Good. When
L equals 2, we can have m sub L's of negative 2, negative 1, 0, positive 1, positive 2, for a total of 5 orbitals there. These are the cloverleaf-shaped, L equals 2.
These are all 3D orbitals, but there are 5 of them. And each one can hold 2 electrons. So here's a summary. Orbitals can be classified by energy, N, and L. We'll get to that in the next video. Shape, which is defined by our L. We have our spheres, our dumbbells, cloverleaf shape, and then many different shapes for F. And our orientation. And our orientation is given by the m sub L. M sub L also tells us the number of orbitals that we have. If we have all 3, that defines that orbital.
Before we go into practice, I want to go back to that previous slide.
Okay.
I just had kind of a thought, because we said that there were a total of 9 different orbitals using the n squared rule. And this is kind of a brute force way that we could calculate it. We had 1 3s orbital, 3 3p, and 5 3d. And if we added those all together, that would equal 9. So if you forget the trick, here's a brute force method. We could get the total number of orbitals.
Okay, so the higher the n, actually n plus L value, and we're going to get into this a little bit in the next lecture, but the higher the n plus L, the higher the orbital's energy. And the energy is really potential energy, so that's distance from the nucleus. And when you have a greater, if you picture the sphere, if your sphere is a greater distance from the nucleus, well, it's bigger, isn't it? It's a bigger orbital. So the greater the n value, the bigger the orbital for any given, s, 1s, compared to 2s, compared to 3s. The shape of the orbital is determined by L, and the orientation is determined by m sub L, which also gives us the number of orbitals. And remember that we have 2 electrons in each orbital as a max. We're going to discuss that final quantum number, because we told you that there were 4 quantum numbers in the next lecture, so stay tuned for that. We have some practice for you, like we always do. We always try to give you some practice. and pause the video and give it a shot.
All right, hopefully after seeing the answers, these will make more sense. It isn't really expected that this is going to come really quick and easy. It took us years of practice to get fluent with it, but you will get it. It's just another one of those chemistry puzzles that takes a little bit of practice and time to complete.
Yeah, it doesn't. It takes a lot of repetitions. You can do it. Just give yourself enough repetitions to learn this material. Thanks so much for watching. Come back again. We'll have some more information about quantum numbers, and then little teaser here, electron configurations coming soon. Bye-bye.